Good day, everyone. Today we will discuss TauNet Genesis Diagram Study Notes. Hello, everyone, and welcome. Today, we're going to explore a fundamental concept behind TauNet, the Tau Genesis Diagram. This diagram illustrates how our revolutionary blockchain begins and evolves with its behavior entirely defined and controlled by its users. We'll start by looking at the two fundamental types of transactions that kickstart this unique process. Two types of transactions. On the TauNet blockchain, transactions are much more than just moving digital currency. The system starts with two primary types of transactions: coin transfer orders and new rule proposals. These transactions are essentially flexible package of information capable of holding elements like Boolean functions, finite bit strings, or tau formulas. Initially, the blockchain specifically processes these two key components within each transaction. Coin transfer orders. The first type, coin transfer orders, is something many of you might already be familiar with. Just like in other cryptocurrencies, these transactions allow users to send digital funds from one wallet to another. They are crucial for managing and updating the balances within the network, ensuring the basic economic functionality of the blockchain. New rule proposals, the power of users. Now, here's where TauNet truly introduces a groundbreaking difference. The second type of transaction is new rule proposals. This is incredibly significant because it means users are not just passive participants. They actively define and evolve how the entire network works. These rule proposals are like submitting ideas for how the blockchain itself should behave, or even how the rules for changing the rules should operate. The Taunet is designed to change itself according to the collective desires of its users, even how their collective opinions are summarized into new global rules. This represents the ultimate form of decentralized governance. So we will look on to the Taunet Genesis diagram, and let's understand the coin transfer on Taunet step by step. So I will walk you in through these 5 steps. First step is your transaction and the local deltas. Second is entering the proposed block. Third is calculating global deltas. Fourth is balance verification. And five is updating the balances. For those unfamiliar with technical details of blockchains, think of this as securing moving digital money from one person to another. We'll trace its journey from the moment you decide to send funds until it's recorded on the blockchain. Step 1. Your transaction and the local deltas. When you initiate a coin transfer, for example, sending digital currency from your wallet to a friend's, your request is packaged as part of a Tau transaction. Within this transaction, the specific details of your money movement are expressed as local deltas. Imagine these as simple instructions: decrease my balance by X amount and increase my friend's balance by X amount. Each local delta specifies the address involved, whose balance is changing, and the amount with a positive sign plus for receiving and a negative sign minus for sending. So let's give an example of local coin deltas. So I assign A for Alice, B for Bob, and C for Charlie. And then this is the address and then the amount of coins. So for here, transaction 1, Alice is sending 1 agoras. Let's say, for example, agoras. Transaction 2 is Bob, and he's receiving 1 agoras and also sending 1 agoras. And transaction 3 is Charlie sending 1 agoras. Step 2. Entering the proposed block. Your transaction, along with many others from various users on the network, is then collected and assembled into what we call a proposed block. Think of this as a temporary holding area or a basket that gathers all the latest pending activities before they are permanently added to the blockchain's history. Step 3. Calculating deltas. Once in the proposed block, the system processes these individual local deltas. For each address on the network that is involved in any transaction within that block, it calculates a global delta. This global delta is essentially the net change to that address's balance. For example, if you send money in one transaction and receive money in another, the system sums up all these changes for your address to determine your overall change within that specific block. If you send 1 unit and receive 1 unit, your global delta for the block would be 0. Based on the local deltas, Alice's global delta, only delta A minus 1 exists for Alice, so her global delta is minus 1 agoras. Bob's global delta, Bob has delta B plus 1 and delta B minus 1. When these are summed, it equals to 0. So Bob's global delta is 0. This means Bob's balance would not change from these specific transactions as his sending and receiving cancels each other out within this block. Charlie's global delta, only delta C minus 1 exists for Charlie, so his global delta is minus 1 agoras. These calculated deltas, global deltas, Alice minus 1, B 0, Charlie minus 1, are then used in the balanced verification step 4 to check if each sender has sufficient funds, and if valid, to update the current balance table to form the new balance table. Step 5. Okay? So, balance verification, checking for funds. Before any money actually moves, a critical step called balance verification takes place. The system checks the current balance table, which holds the definitive record of how much digital currency every address currently owns. So I make a small here. So for Alice, let's just, for example, Alice's current balance is 8 agoras. Bob's current balance is 42, and Charlie has 128. And then we know that their global delta, Alice minus 1, Bob 0, and Charlie minus 1. And then going for sum. So Alice minus 1, 0, and this one is minus 1. Step 5 is updating the balance. If the balance verification is successful, the system proceeds to update the current balance table. It takes the verified global deltas and apply them to the existing balance. This results in a new balance table, which is essentially becomes the new updated record of everyone's funds on the blockchain. This new state is then recognized as the balances at time t plus 1, reflecting the completion of all successful coin transfers within that block and moving the blockchain's financial record forward in time. So in essence, a coin transfer on Townet is carefully choreographed process. Your instructions are collected, tallied, rigorously checked against your current holdings, and then used to update the shared digital ledger ensuring transparency and security in every single movement of funds. DAO transactions, proposing new requirements on how the network evolves. Previously, we discussed how users transfer digital currency. Now, let's explore Townet's most revolutionary feature: how users propose new rules and requirements to change the blockchain itself. This is where you, the user, become an active shaper of the network's future. Imagine you're not just using a system, but actively helping to write its fundamental operating manual, and it actually listens. We have 5 steps, and we will talk about these steps. Step 1: crafting your proposal in the Tau language. Step 2: packaging your proposal in a transaction. Step 3: entering the proposed block. Step 4: new requirements to agreed new requirements. And step 5: requirements at time t plus 1. Let's start at step 1: crafting your proposal in the Tau language. When you want to propose a new rule or change to Taunet, you don't just type a casual message. You express your idea in the Tau language. This is a special, logical language that computers can understand precisely. Your proposal could be anything from a new feature, a change on how transactions are processed, or even a modification to the rules for changing rules. The Tau language allows you to define the what you want the system to do, rather than the how, which is the intricate programming code. This is often referred to as software as sentences. For example, you might propose a rule like never send private data over the network. The Tau language is designed to allow you to specify such requirements, and the system can automatically ensure this behavior is met, even providing mathematical proof. Step 2: packaging your proposal in a transaction. Just like a coin transfer, your new rule proposal is packaged as part of a Tau transaction. These transactions are flexible package of information capable of holding logical statements or Tau formulas. Your transaction will then be combined with other transactions, both coin transfers and other new rule proposals from different users across the network. Step 3: entering the proposed block. All these collected transactions are then gathered into a proposed block. Think of a block think of this block as a temporary collection of all the latest pending activities on the network. It's like a suggestion box that collects everyone's ideas and actions before they become part of the official record. Transactions on testnet can contain both coin transfers and new requirements proposals. Transactions are logical tuples of Boolean algebra elements, for example, Boolean functions, finite bit strings, of which testnet looks at only these two initially, Tau formulas, tables, or elements of a new Boolean algebra supported by Tau. Tuples are assembled as a table in a new proposed block. From there, coin transfers and new rule proposals are treated differently. Step 4: new requirements to agreed new requirements. During this phase, the system actively helps identify agreements and disagreements among user proposals, forming an opinion map. This unique process ensures that all voices are heard and logically accounted for. If two people disagree, Tao does not revolve the contradiction itself. Instead, it's up to the users, guided by the governance rules, to define how such situations are handled. The system calculates the part that everyone agrees on from these combined proposals. Guided by the governance rules. When two people disagree on TownNet, the system itself does not resolve the contradiction in the way a human mediator might. Instead, it identifies the logical inconsistencies. Guided by the governance rules means that the user themselves, through a collaborative and logical process, define the mechanisms and procedures for handling such disagreements and evolving the network's behavior over time. User defined governance from a clean slate. Telnet is designed to start with minimal or no predefined governance rules. The very first users are responsible for collaboratively shaping the network's fundamental rules, including how rules are changed and how disagreements are to be resolved. This approach means that the entire governance model, including decision making processes, is an evolving output of the user community, not a fixed top down implementation. Collaborative discussion in formal language. Users engaged in large scale discussions, expressing their opinions and proposals in a machine comprehensible formal language known as the Tao language. This is distinct from traditional systems where voting on code changes is often difficult to understand and suffer from low participation. The Tao system actively organizes this information, building an opinion map that details who agrees or disagrees with whom and where opinions overlap or contradict. Self-amending system with laws of changing the laws. Tao is a self-amending system, meaning that the governance rules themselves can be updated and changed by the users over time. This is a core feature that distinguishes Tao from other blockchains, which have rigid rules or require hard forks for significant changes. Users define law of changing the laws, which are meta rules that determine the conditions under which the system's foundational rules can be modified. These can include forever rules that ensure certain critical conditions, for example, preventing dilution of token supply, are always met, rejecting any new rule that contradicts them. 4. Mechanism for handling disagreements and conflicts. While Tao initially requires full agreement, users can collaboratively decide to adopt other consensus mechanism, such as majority rule if everyone agrees to it later. However, we know that there's no single optimal voting system or social choice function. Team-specific configurations. Users can form teams, similar to online groups, and configure their own governance rules within those teams, such as dictating that majority wins for decisions specific to that team. Explicit resolution procedures. When contradiction arises, Tao's logical engine will detect them. It's then up to the users to define the procedure for resolving these contradictions. This might involve Debate mechanism, where users can establish mechanisms for debates, viewing the process as a game with winners and losers. Prioritization, prioritizing which interesting questions or issues take precedence when conflicting rules emerge. Resource based resolution, in situations where conflicting alternatives cannot coexist, users might implement mechanisms similar to Bitcoin's proof of work, where computational resources are used to give preference to one alternative. Application stage safeguards. Before a consensus is officially applied, users can configure additional tests and conditions to filter out undesirable outcomes or deadlocks. In extreme cases where no other resolution is found, a Buridan's mule situation, randomness is presented as a last resort. Delegation. Users may choose to delegate their voice to trusted experts, potentially leading to a meritocratic governance structure where experts' opinions carry more weight. In essence, guided by the governance rules, signifies that Tao provides the logical infrastructure, the Tao language, to detect inconsistencies and allow the dynamic, collective definition of its own operational rules. It empowers users to directly control how the system behaves, including how it handles fundamental disagreements, ensuring that the network evolves according to the collective will of its participants rather than a centralized authority. Let's go to step 5, which is requirements at time t plus 1. For this, so I go to the website of TauNet and then I downloaded the Tau language research theories and applications of Boolean algebra version 0.29, the latest one. And here is the theories of and application of Boolean algebra by Ohada Sor here. And then from there you can go to page 74. It says there to perform point-wise revision. So I check it out and it's what we see here. This formula here is what we see here. Okay. So we will discuss this one. Yeah, this one. The formula in the diagram, which defines this integration, is an extended operator for pointwise revision. So I just typed it out, the formula. So we will talk about this. Here, the psi, this is the symbol psi, represents the new requirement proposal, the update. The phi, here, represents the currently running specification, the old rules. X sub n refers to the input at a given time point n, and y sub n refers to the output at the same time point n. The expression chi x sub n y sub n represents the updated logical condition that governs the system's behavior at a specific moment in time. The updated specification. Chi is the new or updated specification resulting from the pointwise revision process. This specification is designed to take maximal advantage of the new requirements while preserving the necessary behavior from the old rules. In essence, Chi is the complete set of rules the system must follow moving forward. The inputs and outputs, x sub n, y sub n. X sub n refers to the inputs received by the system at a given time point n. In the Tau language, these inputs are typically read from the designated input streams. Y sub n refers to the outputs generated by the system at the same time point n. These outputs are then sent to designated output streams. Meaning of chi x sub n, y sub n. When the system runs, it is executing the updated specification chi. The expression chi x sub n, y sub n represents a relation between the inputs and outputs at that specific moment. In practical terms, number one, it is a constraint. Chi x sub n, y sub n states the rule or constraint that must be satisfied by the pair of input and output values at time n. Number two, it determines validity. If you substitute specific values for x sub n, the input, and y sub n, the proposed output, into the formula chi, the formula will evaluate to either true or false. If it evaluates to true, the output y sub n is a valid outcome for the given input x sub n according to the updated specification. The current input and output pair x sub n, y sub n must satisfy the rules defined by the new updated specification chi. So let's break down this formula step by step. So here, in layman's term, this formula say that if the new rule is possible to obey right now, then we must obey it. So this part checks if the current input x sub n, there exists any possible output t that satisfies the new requirement psi. In essence, it asks, is the new requirement psi satisfiable for the current input? Pointwise revision first verifies if a proposed update is satisfiable as a standalone specification. If the new requirement psi is satisfiable for the current input x sub n, then the system's output y sub n for that input must satisfy the new requirement psi. Overall implication, this clause establishes that if the new rule can be satisfied, the system prioritizes and adopts the new rule's behavior. It ensures that if the update is logically consistent and achievable for the current input, it will be reflected in the system's output. An example of a satisfiable specification would be uh, this O1t equal to 1, where output stream O1 should always be 1. Let me play this one for you. So for example, rule A is the currently running specification. This one here. This is the currently running specification. And then rule B is the newly proposed specification. When we enter this one, O1 T equals to 1, there is a result here. So this is satisfiable. And this is rule C, newly implemented specification, combination of rule A and rule B. This one. In this example, rule A is the currently running tau specification. Rule B is the newly proposed specification. We see that rule B is satisfiable as a standalone specification. Standalone specification means that the rule is evaluated as a complete, independent set of constraints intended to govern the system's behavior, entirely separate from the currently running rule, Rule A. The crucial reason for treating Rule B as a standalone specification is to perform a rigorous technical check, assessing its satisfiability. If the rule is satisfiable in isolation, it means the constraints it imposes are internally consistent and achievable. The notion of satisfiability in the Tao language is defined such that a satisfiable Tao specification can be executed indefinitely, regardless of the inputs given to the specification. This means there is always a sequence of outputs that can satisfy the rule, no matter what valid inputs are provided over time. Conversely, a specification is unsatisfiable if any sequence of inputs would lead to a contradictory situation. In summary, requiring Rule B to be a standalone specification ensures that the proposed update is logically sound and executable on its own before the pointwise revision mechanism attempts to combine it with the currently running rule, Rule A, to produce Rule C. So here, Rule A is the current spec or the running specification combined with Rule B, the new spec or the new proposed specification, results to Rule C, the updated spec. So you can see here, this is the current running specification, and here is the proposed specification, and here is the updated specification. If the rule cannot survive this initial test, it cannot be safely incorporated as it would likely introduce non-executable behavior or a contradiction into the resulting system. Let's continue. So this one, it says, if the new rule is currently impossible to follow, then the system must temporarily revert to following the old rule. Okay. So this part checks if the current input x sub n there exists no possible output t that satisfies the new requirement psi. This means the new requirement psi is unsatisfiable for this particular input. An example of an unsatisfiable specification would be O2t equal to 0 and O2t equal to 1. Output cannot be 0 and 1 simultaneously. Let me show you the video. In the Boolean algebra, 0 and 1 are distinct constant. A condition requiring a variable to be both 0 and 1 at the same time is inherently impossible to satisfy. So it says here F. So here, if the new requirement psi is not satisfiable for the current input x sub n, then the system's output y sub n for that input must satisfy the old requirement. Yeah. So no updated specification. The absence of an updated specification line after this step in the log further confirms that the proposed update was rejected and the running specification remains unchanged by this input. So what is running here is the old spec because the new spec is unsatisfiable. Overall implication: this clause provides a fallback mechanism. If the new rule cannot be fulfilled for a specific input, the system reverts to the behavior defined by the old rules. This maintains the system's operational integrity and consistency, preventing it from entering a contradictory state. Okay. So in layman's term, this means if there is any possible output that satisfies both the old rule and the new rule, then the actual output chosen must be one that satisfies the old rule. This complex part checks if, for the current input x sub n, there exists some output t that satisfies both the old rule phi and the new rule psi simultaneously. This identifies an overlap where both specifications are consistent. If such an output T exists that satisfies both phi and psi, then the system's output y sub n for x sub n should prefer to satisfy the old requirement phi. Overall implication: this is the core of preservation in pointwise revision. It states that when there is an output that satisfies both the old rules and the new rules, the system will prefer to maintain its previous behavior as defined by phi. This ensures that only the truly necessary changes from psi are applied, while the existing, compatible aspects of phi are preserved, leading to a maximal preservation of the previous specification's behavior. What happens when new rules clashes with the old rules? Now let's consider the scenario where a proposed new rule directly clashes or contradicts an existing rule. This is where other parts of the extended operator come into play. TOWNet, unlike systems that might simply resolve a contradiction by external means, uses its inherent logical framework to manage these situations deterministically. Here, let me show you this. Tao's pointwise revision algorithm is designed to handle such conflicts. So you can see here, this is the old rule, and this becomes the new rule. And we can see that um, they are contradictory. There is conflict. If a satisfiable update clashes with the existing specification, the algorithm prioritizes the new update to ensure the overall specification remains satisfiable. Yeah. So what happens when new rule clashes with old rules? Let's go back to the formula. So when rules clash, we look at the first two clauses of the extended operator, often in conjunction with the system's overall goal of maintaining a satisfiable specification. So, prioritizing a satisfiable new rule. The first clause is this one. Okay. This asks, is the new requirement psi satisfiable for the current input x sub n? That is, can psi logically be true at all? If a proposed update is not satisfiable as a standalone specification, no update occurs. If psi is satisfiable for the given input, then this clause means that the system's output y sub n for that input x sub n must satisfy the new requirement psi. In layman's term, if the new rule is possible to obey right now, then we must obey it. The clash scenario. If a satisfiable new rule directly contradicts an old rule, example is this one, O1t equal to 0 and O1t equal to 1. So this is the old rule and this is the new rule. So we can see that they really directly contradict with each other. So what happens? So we prioritize the new, or Tau prioritize the new satisfiable update. The purpose is to ensure that the overall specification remains logically consistent and executable. The optimal revision focuses on what output should the program output now at each point in time. If the new rule is deemed satisfiable, it takes precedence in areas of conflict. This allows the system to evolve and adapt its constitution based on newly agreed upon conditions. Fall back to old rules if new rule is unsatisfiable. The second clause is this. This clause asks, for the current input x sub n, is there no possible output t that satisfies the new requirement psi? This indicates that the new rule psi is inherently unsatisfiable for that specific input, proposing O1t equal to 0 and O1t equal to 1 for an output O1t. If the new rule is unsatisfiable, then this clause means that the system's output y sub n for that input x sub n must satisfy the old requirement phi. In layman's term, if the new rule is currently impossible to follow, then the system must temporarily revert to following the old rule. This clause acts as a safeguard. If a proposed rule itself is contradictory or logically impossible to satisfy for a given input, the system will not adapt it, but will instead revert to the behavior defined by the old rules. This prevents the system from entering an inconsistent or undefined state, a critical concern in logic and computer science. TauNet prioritizes consistency over completeness to ensure trust in its proofs and operations. In essence, the pointwise revision algorithm orchestrates a delicate balance. It prioritizes the integration of new, satisfiable requirements. It falls back to existing rules if a new requirement is inherently unsatisfiable, and maximally preserves compatible existing behaviors. This entire process is grounded in the Tau language's ability to reason about its own specifications and their satisfiability, which is a major scientific breakthrough, enabling a truly self-amending blockchain. This decidable and consistent logical framework allows the system to understand changes and their consequences, adapting its operational code dynamically without human intervention for every update. How these parts work together for rules at time t plus 1. The entire formula defines the new specification, rules at time t plus 1, by combining the old and new requirements through a process known as pointwise revision. This mechanism is a foundational element for TauNet's adaptable nature and smart constitution. It guarantees that the system's output will always be consistent with a satisfiable specification. It prioritizes the new requirements where they can be met. It falls back to old rules when new rules or new requirements cannot be met for specific inputs, ensuring robustness. Crucially, it preserves existing behavior wherever the old and new rules are mutually compatible, facilitating incremental and controlled updates without necessitating a complete overhaul of the system's definition. The Tau language is uniquely capable of this, as it is a software specification language that can reason about its own sentences, specifications, and their satisfiability, treating them as elements of Boolean algebra. This enables correct by construction software that can adapt dynamically to user-defined requirements without requiring centralized coordination or global consensus. The process itself is a fusion of specifications in a logically consistent way, allowing the system to automatically modify and adapt its operational code and behavior based on collectively agreed upon conditions. We've journeyed through the intricacies of the Tau Genesis diagram and explored the unparalleled benefits of its unique transaction types. What we've seen is not just another blockchain, but a fundamentally new approach to technology and human collaboration. TauNet is designed to be fully controlled by its users, adapting and evolving in real time based on their formally defined rules. This self amending capability, built on logical AI, solves the paradox of self amendment, making TauNet an endgame of all blockchains, always new and regenerating according to user desires. It empowers millions to collaboratively define and develop software and to engage in truly scalable discussions, an achievement previously thought impossible. This means potentially bug free software that perfectly matches human intent and an ability to combine human brain power on an unprecedented scale to tackle humanity's biggest problems, such as social coordination and even stupidity. Users define the what, the questions, and the machine provides the how, the answers, eliminating the need for constant human cooperation in discussions as it's done automatically. This vision is not just theoretical. The Alpha Testnet is bringing these capabilities to life, allowing users to experience a system that truly learns and grows from their input. The ultimate success of TauNet hinges on the active participation of its community members. We invite you to be a part of this groundbreaking journey. Your involvement helps ensure the network's evolution and functionality. Please visit tau.net, become a community member, and play an active role in shaping the future for this groundbreaking technology. You can engage with us on Telegram, Twitter, and Reddit, or through our forums where you can provide feature requests and feedback, or discuss development and governance. Your brain contribution is invaluable, and by participating, you directly contribute to a new horizon for society, where technology truly serves the collective will and knowledge of humanity. Thanks for watching.